So you see, you have a cat video. You want to share it with a friend. So what do? You press on the share button, you get the link and you share it with your friend. Those actually summarize those two principles of the centralized web. So the cat video is posted by someone. Someone posted it on YouTube. So because it is inconvenient to host your own server, he uploaded it because, well, maintaining a server is a lot of work. So a lot of people are lazy, so they did the same. Which actually summarizes the first step is those resources, those videos are concentrated on one entity, which is YouTube. So another concept is that link address is youtube.com/yourcatvideo or the personal cat video. This is called host-based addressing, which just means the address of the cat video is based on where it is hosted, which is in this case youtube.com. So what do you need to do to move the video from youtube.com to for example, instagram.com? Well, you have to re-upload it again, which is actually a no-brainer because that's what we do. So you have your video on YouTube, you have your video on Instagram. But what if I told you you can upload it to the internet without hosting it on YouTube or Instagram and you only have one link you need? That's all you need. Welcome to Decentralized Web Magic by Nico Reindl. So I'm a full stack developer, I'm fascinated with decentralization, so that's why I give this talk today. So what do we need? The core, it's all about hash functions. So what is a hash function? A hash function takes an input and produces a fixed length output, typically 32 bytes. So we take this cat, we hash it, and you have the hashed cat, which looks like this. So what? Well, you now have something called content-based addressing. Also sounds complicated, but when we see, first I talked about host-based addressing, which means the address was based on the host, so it was dependent on the host where it is hosted, which was in that case YouTube. And now we have content-based addressing, which means the address is based on the content. So in those hash functions, when you take one input, it always gets the same output. When you take another input, you get a different output. So you never get the same output from two different inputs, which means those hashes are unique. So you can use them as addresses. So it does not matter where it is stored. So there is you. You are in a peer-to-peer network, which means everyone can participate anonymously, like every computer, wherever. So the person can take that video. He can split up the video, has 4 parts, and then distributes it across the network. So in the peer-to-peer network, all those peers are anonymous and untrusted. So in those peer-to-peer network with this unique address, you can get all parts, but well, can we trust strangers on the internet? So how do we establish trust in the first place? This is where Merkle Trees come into play. Merkle Trees allow data verification across peers. So what is a Merkle tree anyway? So a Merkle tree is in essence a binary tree, and except of the values there are hashes stored. So hashes of what? So in the ground layer you have the leaf nodes. Those are those data parts, and the hashes of those data parts is each one leaf node. And every leaf node, 2 share one parent node, which is basically just those hashes concatenated, so added together and then hashed again. And you rinse and repeat and you get something like a tree structure. So to clarify that, let's build one for ourselves. So you have those 4 parts of the video. Everything gets put through a hash function, and you have those leaf nodes. Now you take 2 leaf nodes each. First you hash them, concatenate them, and then you hash them again. So you have those purple dots, which are the parent nodes. You do the same for the 3rd and the 4th part. And then you take those parent nodes, hash them again, and you get the root node. So the cool thing about the root node is it is everything hashed together. And as I mentioned before, when you change the input even slightly, the output is completely different. So when you change one of the root nodes, one of the leaf nodes, the root node changes. So how do you compare those two Merkle trees if they are the same? Correctly, you just take the root nodes, compare them. If they are identical, you can be sure they are absolutely the same. So how do we use it to download files? So you get that root node from a trusted party. Let's say Bob, your friend, sends you the root node. So you trust Bob. Then you go into the network and ask who has files associated with that one root node. So the network responds and you get all those data chunks. So with all those data chunks, you can't be sure if they are correct. Because it's the internet, they're strangers, you can't trust them. What you do then is reconstruct the Merkle tree. So you take all the sets you got, hash them again, get your leaf nodes and reconstruct the Merkle tree. So as I said before, the only thing you need to compare is the root hash with your root hash. So you take the root hash of Bob you got and compare it with the one you got. If they're the same, you can be 100% sure they are exactly the files you needed to download and exactly the same. So with 100%, you can be happy now. So it's cool. You got your 4 parts of the video, put them together, you got the cat video again. Awesome. But you might ask, but Nico, why the tree? Like, why? You could just take all the parts together and hash them. Well, you are correct. You could do that and it would work. So let's say you have like 1,000 files and you only need 2 of them. Well, you have to download all of them to hash them to validate if it's correct. So the thing is, if you only need 2 files of 1,000, that's a drag. So what trees allow you to do is partial validation, which is awesome because you only need the root node of your friend, the relevant parent nodes to reconstruct that root node, and well, your requested files. So if we put that in a tree, you see you only need that purple dot, which is a parent node, your root node, which you got from the files, and those 2 files you request to download. And as you see, you don't need to download the other 2 files to reconstruct the root hash to validate it in the end. So that's awesome. So some examples of projects that use that that Merkle tree is, for example, the interplanetary file system, Ethereum, which is a cryptocurrency, uTorrent, or like Bitcoin. Everybody kind of knows in those days what Bitcoin is. So in Bitcoin, for example, you have the blockchain, and in each block there is a transaction stored, which is that TX0, those blocks. And this is where the Merkle tree is used, for example, in Bitcoins. So to summarize, you have that content-based addressing, which enables you with consistent links, no matter where the content is stored. And you also have efficient verification with the root hashes. So you can make the trustless distribution of those data sets across the network, which are those 2 essences of the decentralized web magic.